Hello and welcome to this lesson brought to you by BitMerge. This lesson is about basic computer organization, including storage and processing. We'll look at the basic organizational scheme for computers and go into some detail about each of the major components. Modern computers are quite complex machines, but they can be understood with a few fundamentals and a lot of layering. Layers are essential to any interaction with computers. While using a computer doesn't necessarily require that you know what's going on under the hood, if you peel back the layers and look at what makes a computer work, you're empowered to make better decisions about how to use your computer, from making choices about what to download and what to avoid, to deciding on a particular memory kit for your computer. Let's start with some basic ideas and work up to a fuller understanding. Every computer has a clock, which is a piece of hardware, an oscillator, that sends pulses of electrical current to all components of the computer at the same time. This clock is measured in hertz, or pulses per second. The time between two such pulses in a computer clock is a clock cycle. This gives us a unit with which to measure how quickly or slowly things happen within a computer's hardware. Usually, we're concerned with instructions, or operations to be performed at the hardware level. Add 10 to 5 is an instruction, for example, and this instruction can be completed within a certain number of clock cycles, depending on the particular computer. Generally speaking, the higher the frequency of oscillations, the more quickly instructions can be carried out, and therefore, the faster the computer as a whole. However, there are other factors that contribute to increased or decreased computational speed. Now that we have a mechanism for moving current throughout the hardware components of a computer, we need a few more things. Most modern computers follow the same organizational structure called the von Neumann model, invented by John W. Mauchly and J. Presper Eckert, and not by John von Neumann, as is commonly believed. The von Neumann model consists of a processor, registers, an arithmetic logic unit, a control unit, input-output capability, and storage media for both short-term memory and long-term storage. We'll look at each of these systems in this lesson. A computer's CPU, or central processing unit, is the real brains of the operation. It is the hardware component that's responsible for fetching data, carrying out instructions, and delegating tasks to other hardware components. Inside a CPU are several components that make it work: registers, an arithmetic logic unit, or ALU, and a control unit. Registers are memory locations within the CPU that the CPU can access most readily. Because registers are housed within the CPU, access time is exceptionally low. Access time increases as components are farther from the CPU. Registers can only store so much data, however, as they're usually quite small in capacity. An average CPU register holds no more than 64 bits, and there are no more than 64 registers in total. Registers are therefore usually set aside for special purposes. Low-level assembly languages can access these registers directly, using an identifier like R0 for register 0 or R1 for register 1. Registers, like other types of memory we'll see in a moment, are volatile. They can only hold information so long as the power is turned on and current is flowing. The moment the power is switched off, the information inside the registers is lost. Also inside the CPU is the arithmetic logic unit, or ALU. The ALU performs operations on bits, using transistors, gates, and small memory stores. Without going into the details of how this works, the ALU is given an input of commands and data, and returns an output of data that is the result of executing the commands on the input data. The control unit in the CPU is the device that tells other components what to do and how to respond to data. The control unit can, for example, instruct data from a register to be processed in the ALU and then returned to another register. A machine cycle, also known as a von Neumann execution cycle, or a fetch, decode, execute cycle, outlines the steps a computer's hardware follows to carry out instructions and run programs using those instructions. The cycle is a 4-step process, begun by fetching instructions from memory. The instructions are decoded in the control unit as commands to the ALU, then sent to the ALU for execution of the commands. The results are then stored in memory. This simple process happens over and over again within a computer, and is what makes the computer run. Because computers can move through the steps of the process billions of times per second, computational power is achieved. The fetch, decode, execute cycle model does a good job of explaining what a computer is doing when it's computing. Understanding this cycle requires some abstraction. It requires that you ignore the specific details of how the computer fetches, decodes, and executes, but can still explain what the computer is doing. Abstraction is everywhere in computers, and actually helps us understand why modern computers are so user-friendly. To browse the internet, for example, the computer user needn't worry about the software that runs the browser, the way the browser's program is converted into lower-level languages, and eventually converted into digital logic in the hardware. At each level of abstraction, the details at lower levels are hidden and irrelevant. More formally, there are 7 levels of abstraction that computer scientists generally agree on. At the very top are users, who deal with executable programs. Moving down the levels of abstraction, there are high-level languages. Python is one example of a high-level language that we'll look at in other lessons. Assembly languages, which deal with assembly code. System software, the programs that run your operating system and other system-level programs. Instruction set architecture, the methods and rules that software and hardware use to communicate with each other. Microcode, which is essentially the hardware implementation of low-level machine code, and digital logic, which includes the logic gates and circuits used at the lowest level to move, manipulate, and store bits. The interface between software and hardware becomes quite important when input and output devices come into play. Software needs to be built to handle key presses on a keyboard or clicks on a mouse, for example, which are registered in hardware as electrical signals. Displays, such as monitors, are likewise hardware devices that are supported by software. An input-output system to handle these and other devices is crucial to the function of a computer if it's to have any human users. With an understanding of how the CPU delegates and carries out instructions, let's turn our attention to memory and storage. Memory solves the problem of holding on to data so that it can be used for computations. Luckily, at the user level, you don't need to worry too much about memory. Programmers do have to worry a bit more about memory, however. When somebody mentions memory in the context of computers, RAM is usually what's meant. RAM is primary or main memory and stands for random access memory. The name refers to the ability for cells within RAM to be accessed randomly using a system of addresses. RAM holds a certain number of memory cells of a given size. Each cell is given a unique address. Address systems generally start at the lowest memory address using 0 and then move upward 1, 2, 3, and so on. RAM uses transistors paired with capacitors, which lose charge over time. RAM is therefore volatile, just like registers in the CPU. The bits in this type of RAM, called dynamic RAM or DRAM, need to be constantly erased and rewritten. Static RAM, or SRAM, on the other hand, does not need constant refreshing, but uses more transistors per bit stored. There are subtypes of each of these, but in general, DRAM is good for desktop computers, while SRAM is better suited for embedded systems, like the much smaller computers that run calculators or toys. All RAM is good only for short-term storage, as information stored is lost when the power goes out. Luckily, RAM makes up for this limitation in speed. It's not quite as fast as the registers in the CPU, but it's faster than a hard drive. All the information needed for a program that is currently running is ideally all located in RAM, though this is generally not the case in practice, as RAM can't hold unlimited data. Often, whenever a computer is processing data, it moves needed bits to RAM, but actually moves more data than the program initially requires. This is because of the locality of reference principle. It assumes that neighboring memory addresses are likely to be used in sequence and within a short period of time. Preloading data expected to be used results in saved processing time. Let's take a step back. The systems we've just seen are the CPU with its registers, control unit and ALU, input-output devices, and primary memory. These systems are all connected via buses. In modern systems, there are 3 buses that connect them, each with a specific purpose. One for data, one for addresses, and one for control signals. What's left for us to discuss is a long-term storage medium, a hard drive. Hard drives, or hard disk drives, are long-term, non-volatile, or persistent storage media. That is, they store programs and data for long-term use, and do not lose the information when the power is turned off. The access time for data on a hard drive is called seek time, and is much slower than the access time for primary memory and registers. Hard disk drives use stacks of spinning disks called platters, each with billions of bits stored by magnetism. A bit is either a 0 or 1, depending on whether or not it's magnetized. A read-write head scans over the platters and converts bits to electrical signals to write bits to the platters, and converts magnetized states into bits to read from the platters. Solid-state drives, on the other hand, do not have any mechanical parts. Instead, they use integrated circuits and transistors designed in such a way that they do not require constant refreshing like RAM does. Now we've looked at just the basics of computer organization, but you should have a fuller picture of how a computer works from this lesson. You should be able to recognize that parts of a computer do not work as individual units, but are really connected in meaningful ways to produce a dynamic machine.